We have Andrew Hay and T-Boy Roy here presenting on Unveiling, the open source visualization engine for busy hackers. So proud to present them. Take it away, guys. Thank you. Thanks.
Hello, Las Vegas. Hello, Black Hat. We're super excited to be here. This is the first time we actually present here. This is a very visual presentation. We prepare a lot of very interesting data sets. We really hope you guys are going to really enjoy it. So let's get started. Allow me to introduce myself real quick. So I'm Thibaut. I'm a security researcher at OpenDNS, and I used to work at NVIDIA for like 3 or 4 years. And then in order to introduce myself, I love to answer this question, security and visualization, because I just get it all the time. How is that connected? Where did it start? Well, the answer is the demo scene. If you guys remember, the time where we used to download pirate game, actually we still do it. Well, it always came with computer-generated animations that were really nice, and I completely fell in love with that. And I was like, man, I need to teach myself the OpenGL stuff. That's how I got started.
My name's Andrew Hay. I'm the Senior Security Research Lead and Evangelist at OpenDNS, formerly of CloudPassage, 451 Research, a bunch of other companies. So welcome. That's enough about me. So this is the agenda. We are going to go through, like Thibaut said, this is a very highly visual presentation. So there's a lot of data sets that we're going to visualize, which should, we hope, give you an idea of the kinds of things that you can do with the tool. So why visualize the data? And this is something that, I've been talking to press this week and to reporters, friends, colleagues, and they're like, well, why? Why do I care to visualize the data? And, pie charts are great to articulate very small data sets. And by the way, this is the only real good use for a pie chart, to show how much pie you have left. But the visualization actually lets us articulate the data. We can take the very advanced data sets and see what patterns might pop out. So you can use R. I know, is anyone here a data scientist? Use R? Yeah, ping. All right. So a lot of people use R to crunch considerable data sets, visualize them, but that's great. You still need a lot of background in understanding the R language. And Excel, sure, you could use Excel until you run out of memory, or, pivot tables are great, but only so great. Because really what we want is this Minority Report dashboard. And those of you who know me, I've been trying to pimp this to vendors for years. Like, give me the Minority Report sim. I want to take my logs and throw my alerts around the screen, and nobody's done it yet. So this is what I want to do with the data. And looks like we actually can do quite a bit of this now. So I want to talk a little bit about learning styles. And if you've ever seen this VARC model, very common. And it's also very, very controversial because some people do not believe that there is such thing as a visual learner or a tactile learner. But I myself, I'm a visual learner. All my life I've been forced to, read this book 3 times, write it out 3 times before the exam, and you'll memorize it. That's only so good for me. So some people are visual learners, and what we want to do is give people a tool that can use this visual mindset to pick things out and actually do stuff with it. So of the learning styles, the easiest way to think of this is a graphic organizer. And you can take your visualization of knowledge, concepts, thoughts, data, map them all together, and group your like data together. And perhaps the best method for this is just doing a mind map. Has anyone sat down, figure out, okay, I need to figure this out, I'm going to put together a mind map. It's great for presentations, great for startup ideas, new products. It's a very visual way of trying to lay down what you want to do. This is good for blogs too, if you ever want to do that. So what we want to do is we want to clarify that meaning by mapping the relationships. What relates to one another? And if we can represent that spatially in 2D or 3D, we can really focus on the meaning of the data and of the results that we want to see. And we really want to take that visual mapping and present it so that it not only means something to us, it means something to the next person and the next person and the next person. So in terms of fundamentals, I'm going to hand it over to Thibaut. He does all of the physics and math questions. That's definitely not my area. So here's Thibaut.
Absolutely. Thank you, Andrew. So one thing I would like to talk about is, Andrew just said that data visualization is all about representing knowledge. But before we actually go deep into the subject, I'd like to cover a couple of fundamentals. So what is knowledge in the first place? Turns out that semantic networks are one of the most beautiful data structures out there to represent knowledge. You know, it's very simple. It's a network where all the nodes represent concepts and edges represent relationships. And it's like, in other words, a model of the information you're trying to look at. And in terms of data visualization, we're interested in the ontology, which is the model of the model. So when you look at the model of your data, and you can find like hidden patterns, clusters or stuff like that, then you're pretty much interested in the ontology. So a semantic network is a graph. So what is a graph? Let's go back to graph theory 101. Very simple. It's a set of nodes and a set of edges. As you can see here, I defined a couple of nodes here in the vertices, 0, 1, 2, 3. And then all the edges, 0 is connected to 1, 0 is connected to 2, etc., etc. And that gives us this representation. Now, you may not be aware of it, but graphs are everywhere. They're, implemented in a lot of very modern problem solving, a lot of different things. For example, social networks is probably the most obvious one, where you have a graph of people, their friends, their husband and wives, they share different kind of relationships. Obviously, Google Maps, the maps and the shortest path problem, where you actually have to find your shortest way from point A to point B in the least amount of time. Or programmers are probably super, know this one very well, the UML software design diagrams. Or neural networks for any kind of classifiers. So, as Andrew said, pictures is worth 1,000 words, so let's just go through it. So what you're looking at here is an abstract graph. It doesn't represent anything. It's just to show you what the engine looks like, different dimensions where you can map your data on. So as you can see here, you have a couple of nodes, different colors, different shapes, and you have edges, same thing, different texture, different icons on them. And then you have particles floating on the nodes, on the edges, sorry. And we call that the edge activity. And same thing, you have those circles, around the nodes. We call that the node activity. So essentially, you can map any kind of data that you have, onto this graph and the different features of the graph. So allow me to introduce Open Graphity, which is our data visualization engine that we've been working on at OpenDNS for a while. It's free, it's open source, it's public now, it's on GitHub. I will give you the address a little bit later. And it helps you visualize and manipulate any loosely related data. It offers a very easy to use framework and API as well. Let's go over the framework real quick. So I'm going to read this diagram from left to right. So at first we have a 3D engine, Raindance, that leverages OpenGL ES, GLM Math, and OpenCL acceleration. Then Open Graphity, our engine, sits on that 3D engine, does data visualization, specialized in graphs, and offers different kind of APIs. Can be compiled two ways, using CLang++, and then you obtain a binary file, which can use the Python scripts. Or you can actually use EM scripting, that's going to transform your C++ code into LLVM bytecode, and you can actually integrate it in the web with JavaScript. And finally, we have SemanticNet. That was a Python library that was developed at OpenDNS as well. It's completely homemade, and it helps you create your graph data sets and store them into the JSON format. It's very simple, and for those of you who are familiar with NetworkX, an amazing graph theory library, well, we use a lot of that as well. And finally, you can use this SemanticNet library, to create any kind of data set, like raw to relational, any raw to relational approach, the ripple effect, and the random walk. We're gonna come back to it later.
So Unlike most tools, it was actually developed to work on a Mac, first and foremost, because that's what we use at work. You know, we're in San Francisco. Every startup is all Macs except for like 2 guys that just won't give up their Windows laptops. But also compiled and works on Linux. You require Python 2.7. So if you're like me and you're, you know, a Rubinista, then you got to learn some Python and or some JavaScript. Very easy to build. Just clone it from the Git repo. Make sure to use -- recursive. Install NetworkX. Go into the directory and then make clean native or make clean web. Might as well go make clean native. That's going to be your standalone client. When you make clean web, that's for the webified version. So this is really the workflow of the data. So we take your loosely related source data, so a CSV, JSON file, any data source, flat text file, convert the data into a format that uses the graph theory and the physics and the math that we can pull into the engine to visualize. And then once we have it actually represented in the engine, we can then manipulate it further. So again, simple graph theory 101. This is how you would use semantic net to convert your data to the format that is supported or required by Open Graffiti. So as you can see, we have nodes, we have edges, we have labels. Very easy to go through, and you can build very complex graphs without having to relearn, you know, a completely new data language. And to run it, very easy. Like most Linux, Unixy applications, demo is the default package that is shipping today. There will be more added for additional visualizations, you know, maybe clustering and, you know, open source, unlimited possibilities. So if you're a data scientist or if you are a security analyst or just a developer, all of the plugins are written in Python and soon to be JavaScript. But what you can do, so we rely heavily on NetworkX, but these Python scripts and JavaScript scripts, that's kind of meta, you can see here on the far right hand side, these are the scripts that you use to manipulate the data once it's already in the engine. So left hand side, we have the different layouts. You can make your nodes bigger, smaller. You can make the lines thicker. There's additional attributes which will allow you to show particles flowing between the nodes. There's an animation link that will take your graph and, you know, just have like a continuous spin. You can actually see it at our booth. We've got it running there as well. And then a timeline if you want to create a time series graph. So I'm going to pass it back to Thibaut for the physics part.
Absolutely, thank you. So Andrew just explained how you can create, you know, very easily a data set from your own data. But, you know, how do we transform this converted data into the 3D representation? Well, it's very simple. We use some particle physics. So don't run away, even if you're not good at math. It's
some simple particle physics.
So as you can see here, the concept is very simple. The formulas may scare you, but the concept is super simple. All the nodes that are connected attract each other, and all the nodes that are disconnected repulse each other. It's as simple as that. As you can see, for the math nerds out there, we have you know, 2 different forces, attractive force and repulsive force. They all depend on distance between the nodes. And then you have pretty much a K constant that depends, you know, on the area divided by the number of nodes. In other words, the density. And so we pretty much, so it's like a kind of simple formula to, you know, play with the density of the layout. Essentially, when I change C, I can, you know, control how dense the 3D layout is going to be. So yeah, that's super simple. So at first we start like this. We put all the nodes in the same place, and then we let the physics run. So as you can see, start expanding. All the nodes connected to each other are going to pretty much stick with each other, and all the nodes disconnected is going to repulse. So I may notice here that you will see this molecular kind of shape layout, which makes complete sense because the force-directed algorithm is inspired by the celestial body's forces, or also electrical forces. It's not exactly the same model because it's way too complicated to implement on a CPU, but still it's the same concept. Also, you may notice here that the nodes start vibrating. So what does it mean? It means that all the forces are becoming even, so it means that the graph has reached pretty much the equilibrium. Usually it means that you have a visually pleasing layout. All right, so obviously in this demo, the process has been slowed down just for, to show it like more obviously. Then I would like to answer this question. Why do we do this? You look at it and you're like, okay, that looks pretty cool, but what's the point? So in most modern, problems, graph-solving problems that we have today, we have actors populating a graph, a knowledge graph. It could be a relational database, anything. And usually, the creation, of the nodes, or like all the entities of this graph is very well understood. However, the output is complex because usually your actors are humans, cars for Uber drivers, for example, or dogs, cats, whatever, any kind of service you can imagine. So using that kind of layout gets closer from what I like to call the natural shape of the data structure you're looking at. Because the layout depends on all the forces, and the forces depend on the nodes and edges. So obviously the layout is going to show you the structure of the data structure. And also, GPUs have become so fast, insanely fast at doing like vectorial computation. So that's why we love to use the GPUs to entangle the information, to use this force-directed layout. And finally, Andrew spoken about that a little bit earlier, but humans are so much better at processing shapes and colors instead of just text data. All right, so that was all the fundamentals part. Now let's move on to
now the fun part.
To the fun stuff.
Yeah. Thanks for sitting through Graph Theory 101. So we are going to look at some data sets, and the biggest question of any new tool is, all right, well, how can I apply this to my data set, not just some canned data set that you're giving me to show me, pretty pictures. So what we've done is created a wide variety of data sets that should show you how easy it is to link data, link nodes to edges, just link A to B, B to C, C back to A. So the first thing we're going to do is we went to a number of security vendor websites and we looked at their partners page. And we've identified what partners they have listed. Now this is not exhaustive. Will, who compiled this, he did this while his wife was watching TV one night. And so he only got so far before he just gave up and stopped doing it. But we can actually see what companies that we've looked at share partners. So this is very basic, high-level data set. And as you can see, it is visualized. It'll zoom in here in a second. And we start with OpenDNS and who we have partnerships with. So all of the red nodes are the companies that we actually checked. We checked their partner pages. All of the blue nodes are the actual partners. So you'll notice that Norse has a bunch of partners, Vertisys, some of these, like Juniper, obviously has a lot of partners as well, but it's not one of the sites we went to and checked their partner page. So does everyone get this? Very high level, shows what's going on. Palo Alto Networks, a bunch of others. And all of this zooming in and flying around the graph, this is all done by the analyst or the data scientist at the keyboard and mouse doing all this. Does anyone get motion sickness? No? Good. So that was the partner visualization. Again, very high level. So I used to be an industry analyst. And we were always talking about, who's going to buy who for what money, who have they bought in the past. So took a look at all of the merger and acquisition activity since 2002 in the security space. And then we connected the acquirers, who was actually doing the buying, the targets, who was getting acquired, and then, if disclosed, the acquisition value. So by looking at this, it looks like a celestial star field. And what we have is the white nodes are the acquirers, so the company with the money. The green are the targets that were acquired, and then you'll notice, hopefully you can see this, there's a particle that goes between the acquirer to the target. So that is the value of money paid for the acquisition. And the faster the particle, the more money that was paid. So to give you an idea, you'll see companies here like Symantec and all their acquisitions, Cisco, but then you look at like McAfee and Intel, and the money that went from Intel to McAfee, and it's just going crazy. Whereas, it kind of sets the speed for all the other particles in this graph. But again, if you're a startup and you want to see who should acquire you or who you want to acquire you, there's actually a good way to say, okay, well, they already have one of me or something like my technology. So I'll look for someone else who apparently has a lot of money to throw around and has done so. Something that I want to do with this data set in the future is tie it into Crunchbase so that I can take all of the venture capitalist firms and how much they invested and then see, who are the 3 VCs you need in order to get acquired by company X? And how much do you have to raise in each round? So look for that. So that is really another idea where it's abstract data set, nothing to do with security, but should give you an idea. We've got the target, we've got the acquirer, and then we have the concept of the value paid for the particle speed. Another data set is, so there's another functionality, or another piece of functionality of the tool where we can represent what changed between one data set and another data set. So we call this the diff graph. And for our example, we took the Ukraine autonomous system number internetwork. So this was taken from, June 24th to July 8th. And what we have is, if the node is green, they're additions to the network. If they're red, they're subtracted. And there are some that are yellow, and those are just modifications. So maybe there was a new route added or a new set of IPs or just something changed in that AS. So to give you an idea, this is what the original Ukrainian AS network looks like. And this was taken recently, a couple weeks back, maybe. So as you can see, the ball at the bottom, that is what AS?
9002, RETN.
Yeah, RETN, AS 9002. So that's the Comcast of the Ukraine. So a lot of home users. Yeah. It's Comcast of the Ukraine, but with better customer support. So if you want to take a look at what has changed, like this is a lot of data to go through. So why don't we see what happened from a different period of time or across a period of time across the data sets? So as you can see, it's a much smaller graph. It has the green additions, the red deletions. You can see the same format or the same visual design from the last one applies here. It's just upside down. But it's very easy to see what has been added and what's been subtracted. So think of IDS alerts or firewall rules. If you're visualizing firewall rules, hey, why were all these firewall rules added around the same time or in this time frame? I'm sure there's Jira tickets for all the firewall rule changes anyway. So that's the diff graph. Now something else which we thought would be really cool is to take a tool that everyone uses for system and application intelligence and visualize it so we can see what's going on. So we took the Shodan API and we actually wrote a Python script that's going to be released with the SemanticNet part of the SemanticNet library package that allows you to run your query just as you would within Shodan using the API and then pull the results back down, format it in a way that can be ingested by OpenGraffiti and you can visualize it. So, has anyone here not heard of Shodan by now? Great tool. Yeah, not a single hand. Or who doesn't want to admit that they don't know what Shodan is? All right, one person. All right. So what this looks like, apparently a lot of people want to know which webcams are open and are accessible on the internet. I'm not sure why this is. I'm sure it's for research purposes only. But what we have here is the search string. The common banner is this video web server in the center. And what we've taken is that search string and it's blown out to the common port numbers. So you'll see linkages in port numbers. We have ASs. Then from that information, we can actually determine the country of origin that it resides. So here's an example, port 80. Surprise, surprise, a lot of cameras on port 80. But there's also alternative ports, 8080. I believe there's one that is just 81. Yeah, that's it. Nope, that's 8080. And as you can see, we have IP address, the AS number. Yeah, there's 81, so very few. But what this highlights is the commonalities based on your query of the Shodan data set. And so we've been working pretty closely with them. They are chomping at the bit to get this and use it for other data sources. But it makes it really easy. So if you don't know any Python at all, but you want to visualize something really cool, the Shodan script is there. So you just run your query, ingest it, and you're good to go. So that is the Shodan query that is visualized. So another data set which we've used at OpenDNS is this nuclear exploit kit, no L. And what we have in our visualization is we have the domains that are hosting the EK in pink, and then the IPs in yellow that are retrieving. And what we have is just a domain to IP graph. And what you'll notice here is you can quickly see the clusters. So remember, pink is the EK, and yellow is the IP. So this is just to show you that we can take very high-res screenshots, and it may not show up as high-res, trust me, it's high-res. But you can take your data sets within Open Graffiti and export them to a PDF, PDF, SVG, there's multiple output formats. We will be adding more as time goes on. But yeah, high-res screenshots. I will note that at OpenDNS, we have pictures like this of data in every single conference room, and we could probably start selling them. So that is the nuclear exploit kit. So who here's heard of the Verizon DBIR? Yeah, only 2 people, okay. Yeah, very popular report, comes out once a year. It helps define spending patterns and marketing buzzwords for the rest of the year. But it also shows us a lot of breach information. So what we have done, and all of the data for the breaches is posted to vcdb.org and their GitHub repo. And using the Veris vocabulary for event recording and incident sharing, and the VCDB, lots of acronyms, what we can do is we can actually group and articulate some of the clusters of similarities between the different breaches. So this is a very big data set. And what we have is in green, those are the companies that were breached. White is the method of breach, or the reported method of breach. And so as you can see, one of the options, wiretapping, surprisingly high number. I was a little surprised by that. And what we have in the red is the asset or the item that was breached or that was involved in the breach in some way, shape, or form. So you'll probably notice a lot of companies here that you may do business with, you may not do business with anymore. But what really stands out is the clusters. So you can actually see, like this articulates, if someone says, well, this type of breach, I used to work at a bank in Bermuda, and the response to buying new security equipment was like, well, why is someone going to attack us? We're a bank. Once we got past that, it was, well, we're surrounded by water, so no one's, we're going to be fine, because internet can't cross water. But this shows you, if you are a bank and you know some of your competitors or organizations that are very similar to you, and they show up in a cluster with a whole bunch of other breaches, that may be where you want to put some of your spending in from a defensive standpoint. So very great visualization, great data set to work with. I want to thank the guys at Verizon. The DBIR team was very helpful with this. Fantastic. Boop. Come on. So the next data set, I'm going to let Thibaut talk through it because it is pretty cool and he articulates it very well.
Thank you. So yeah, for the next data set, we were interested in combining two sources of information, two different libraries, So what we did is we took a text, and you'll see the Hacker's Manifesto. I'm sure you guys are familiar with it. And then we use, the natural language toolkit. For those of you who are not familiar with the NLTK, it's pretty much a parser that can parse human languages, like English, Spanish, Chinese, whatever. And then we create a Markov graph of the words. It's almost a Markov graph. So for example, the sentence, I have a dream, becomes node, I have a dream, and then all connected together. And then finally, we use NLTK to give us the NLP types, so the natural language processing types. So it's very simple. In a sentence, different words have different functions, nouns, adjective, prepositions, stuff like that. So NLTK helps you to visualize that. So the next graph you're going to see, the NLP type has been mapped onto the color of the node. And then finally, we can play it over time. Let's see what it looks like. So again, at first you have all the nodes, like the complete text, the Hacker's Manifesto again. So you see all the nodes, connected, all the sentences connected together, and also the colors representing the NLP type. So usually you would see like nouns having the same color, or like preposition or whatever. So then we activate the timeline, and we start playing it. So as you can see all the sentences, like the words being spoken. Like in the bottom left, you see all the words, and you may remember that amazing
Hopefully that shows up.
Yeah. So yeah, it's super easy and super interesting to look at, because a lot of SEOs use that. They do context extraction, all the search engines. Anytime you have like some study of the semantic field, like lexical field of a text, then pretty much you can use an NLTK to do that. So it helps you visualize the results of a parser, a complicated parser actually, and put it into form into a 3D shape. And also you use a timeline visualization to map events over time. So it's fairly easy. We just take all the words and we activate their visibility over time. So you can see on the bottom right the timeline plane. So you see the sentences being cut at every space. So yeah, super interesting data sets to combine open graffiti with NLTK. And that was over time. Now I would like to talk about something a little more serious. Data goes supernova. Let's face it, in all modern systems, we need much more than a couple thousand nodes. And whatever you do, no matter how hard you try, there's always going to be a limit at your visualization engine. So how do we deal with that? Well, there are like three generic approaches, like three big paradigms. The first one is grouping, right? Entity grouping. Second, sampling parallelization. So let's see what they mean. Entity grouping, well, that's pretty much, we already had some examples in the previous data sets. It's pretty much taking a look at a higher level, and grouping nodes together. For example, if I have a graph of a large company with all the employees, then I'm just going to look at the teams, and that would reduce significantly the amount of nodes. So and I'll still be able to see the general pattern, the general clusters of the company. Then sampling. Since we cannot look at everything together, we're just going to focus on certain parts. So for example, techniques such as the breadth first search, so which is you start from a node where you focus on, take all the neighbors of the neighbors, neighbors and neighbors, etc., etc. That's what we also call the ripple effect, because we go by ripple. And also the random walk is pretty interesting. You start from a node, for example, inside your huge graph, and then you select a random path, and you do that several times. So for example, the result would be the sum of all the different random paths inside a graph. So a good analogy, if you consider the graph of all the streets in Las Vegas, and let's say you were completely drunk last time at Black Hat party. Well, when you try to find your way home, that's pretty much what a random walk will look like.
It's more of a random stumble.
So yeah, and then the other paradigm is parallelization. Once all hope is lost, to reduce the amount of data without losing significant information, then we can parallelize the computation. Libraries such as OpenCL, which expose it. There are specifications actually. But yeah, they exposes, different work groups, different work items, and you can pretty much divide your computation between all the different work items. Also, there's the memory problem. In OpenCL, you have 3 types of memory. So global memory, local memory, and private memory. The private memory is super fast to access, and the global one is very slow. But obviously, the global one is easier to access because it just stores everything, where the private one, you'll have to, divide everything into the different cores and threads. So these were like the big 3 paradigms of, the approach to big data visualization. Now we would like to talk a little bit about our use cases at OpenDNS, because we have, the same like big data problematics to visualize, our DNS data. And I'm going to let Andrew start with that.
Yeah, sure. So we chose these data sets because obviously they're the ones we're most familiar with, and we can really, we know what they are, what they should look like, and then can really talk through them for the different types of visualizations. So what normal people will do is go to the Investigate dashboard and search through our 50 billion queries that we record every day from our users. And seeing 2% of the world's internet requests gives us a nice little database of stuff to poke around with. So this is what the UI looks like. If you look at the very bottom right-hand side, you can see the co-occurrences and the related domains. So what we did for a data set is we took this we took this data set of people that visited blackhat.com, where they visited before going there and then after going blackhat.com. So you've got this huge network, and this is based entirely on DNS queries. So unsurprising, I'm sure to most of you, that a lot of people that went to blackhat.com also went to defcon.org. They also went to bsideslv.org. So obviously, a lot of conferences happening at the same time. People are going to look at all the different talks across all 3 and make their decision. Something else you'll notice is that, as we drill in to Black Hat, you can see the IP addresses of certain sites, actual domains. But look at this one, emailtrack.com. Is anyone going to a party tonight and click that link, the register now, and you get redirected 6 or 7 times through some tracking software? Well, yeah, those are some of those domains. Surprise, surprise. So yeah, those show up quite a bit. So another data example is CryptoLocker. Has anyone here been lucky enough to have been affected negatively by CryptoLocker? One person? Yeah, it's not great. So what happens, completely high level, usually you will get an email get an email with an attachment, you execute it, it will either fetch the malicious CryptoLocker executable, bring it down, run it, start encrypting all your files. Or it could be, the encryptor itself. So there's the nice little red screen. This is kind of what it looks like on most releases, but saying you have to pay the ransom, you don't pay the ransom by the time it runs out, you're never getting your data back. And what happens is these hosts will communicate with DGAs for the key generation to actually encrypt your files. So what we've done, and these are great examples of using BFS and random walk. So this is what CryptoLocker looks like using BFS. So as you can see, lots of clusters, the benign ones off in the distance, very far. The distance that the clusters are from the center actually shows, they are more benign the farther out you go, but still clustered. And these are all the DGAs, the domain generation algorithm dynamically generated domains. So it's very obvious to see, looking at the red nodes, the infected. So these are the CNC domains. So maybe this isn't aesthetically pleasing, or you can't derive the information that you want by looking at the BFS model. So let's take a look at the random walk. So this is the exact same data set using random walk, and I prefer this one over the BFS just because of the obvious format or the obvious pattern that emerges when we look here. So again, red are known DGAs. The pinkish ones are, they could be, they require a little bit more investigation, and then the white ones are benign domains. And does anyone notice a pattern here? So this worm kind of pattern from the center where all of the groupings are. So obviously very red infected domain, but not a lot of communication or links to other sites. But the pattern, what stands out to me is I've been watching a lot of Breaking Bad lately, and so it came to mind when I saw this that what they did was in Walter White they injected dye into his lungs. It only highlighted the tumor and not the other tissue, and that's kind of what this does, because you can see very quickly in the center the main concentration. So with a little bit more research, we could probably say, okay, this pattern looks familiar. This is likely a huge DGA CNC infrastructure. So it's kind of like a worm. So that was some of the security graph data. So again, really cool data to play with. Gives us a lot of fun things. So now we're going to visualize the internet. And I'll let Thibaut jump in on this one.
Yeah, thank you. So the previous data sets, CryptoLocker showed some sampling methods, the BFS and the random walk. Now we are going to the third paradigm, the parallelization part. So we were really interested, in visualizing the whole ASN network. So for those of you who don't know, the ASN network is a collection of connected IP routing prefixes. It's in other words, like the backbone of the internet, the higher level routers. So the graph, the ASN network has, the most recent one we've extracted has like a 55,000 nodes and like 100,000 edges. So how do we visualize that? We are super interested to see, the internet and the structure that it has. So we use OpenCL. So this is a video showing you, what it looks like when you actually start the OpenCL iterations. So keep in mind that this layout is not really eye candy because usually it runs offline, and it's also mostly focused on performance and not really on eye candiness. So you can see here the first iterations of the force directed, except that it's running on a GPU and runs on the NVIDIA GTX 550, so it's 4 years old. So that goes on for an hour. And the result is this. So it's a super interesting shape because you can see, the structure of the ASN network. As you can see here, there's a very, very densely connected core. Most of them are tier 1 nodes, tier 1 ASNs. And then around it, you have the tier 2 and then finally the tier 3. So it's super interesting to see that distribution. And I cannot go super far into details here, but if you're really interested in knowing more about, this ASN network and how we can do malware, detection, we have another talk tomorrow with Dia and Andre Tung, OpenDNS also engineers, and we've done some research on this big ASN network. So please come see us again and you'll see more insights. And finally, we can have high resolution pictures, on this big ASN. So we literally taken pictures of the whole internet. This is what it looks like. So the core here is even more apparent. It's very interesting data set here. So the tier 1 nodes super, super bright. And then around kind of the tier 2 nodes, providing some services to tier 3 nodes again. Very amazing. I'd just like to take a second, to think about all the network engineers, that with their own hands, like they build this internet, and we can finally see it. It's so beautiful. And that was the internet. So 55,000 nodes, 100,000 edges using OpenCL. Now, Andrew, what else can I use Open Graffiti for?
Well, Thibaut. This is Dave Lewis, by the way, on the bottom. So we have provided several scripts to give you an idea of how to create the data sets from data that you might, just stumble upon or use in your day-to-day. So the FS graph, this is actually a file system Python script. So you specify the directory, and you can visualize all of the files and the entire directory structure. So it will show you very quickly the linkages between the files and the directories and subdirectories. So the Python script, very simple, not many lines of code, and should give you the basics that you need to link data that is similar to one another. The showdown query, we provide that as well. You just need to make sure you get your own API key. We're not giving you ours because they'd kill us. But yeah, you just open up the file, put your API key in, start running some queries. It's amazing, the data and the results that you get back. And anyone here use Bro IDS? Yeah, great IDS. This script allows you to visualize the logs. So you can take, I think the sample that we had was, quite huge, 2 different instances over 2 days, and we were able to visualize them using that script that served as the basis for visualizing or creating the script. So again, there's also under the semantic net examples, there's a whole bunch of other Python scripts to show you what to do. There's some sample data sets in there as well. And we hope that it gives you enough information that you can start creating your own scripts. So you can take network packet captures, IDS alerts, any sort of environmental data. This is where a lot of the big data platforms come into play, is in like the pure sciences. And you can also use odd data like the migratory patterns of African and European swallows, which in hindsight we probably should have visualized, because I think that'd have been great. So in terms of what's next, so this is the 1.0 release. It's up on the website now. It's in Git. Went live kind of last night-ish. But this is really just a start. So Thibaut's going to talk about what's coming next.
Absolutely. So next, we'd like to take it to the next level, obviously, and we want to use some virtual reality devices. A lot of data visualization UIs are still all completely designed in 2D. And now in 3D graphics, there's a common misconception, which is, for example, you watch a game, like you play a game or whatever, and you're like, oh, that's 3D. It's actually not 3D. It's like projected 3D onto a 2D screen, flat screen. So to really make it 3D, we need to use those next generation devices like the Oculus Rift, or the 3D vision glasses from NVIDIA as well. That's like a first start at least. And finally, the Leap Motion, which is like this very cool device that like lets you use your hands, instead of using your mouse and the keyboard. So yeah, we really would like to push the experience into some virtual reality immersion inside your own data. So if you guys...
one point here is that when Dan Hubbard, our CTO, told Thibaut that he had both of those devices on order, it was like a 3-year-old on Christmas morning. Never seen so much happiness come out of one person.
That is true. So yeah, if you guys remember the Lawnmower Man, well, it's pretty much where we want to take it.
With less murdering and crazy. Slightly less murder.
So yeah, there's a lot of cool things coming, but the main thing I want to emphasize, and I would like to thank Skylar, our intern, who's worked has made amazing work, on the semantic net library. But the main thing I would like to point out here is we've decided to open source this thing because we know that cannot really work, or cannot really blow up, without the help of the security community, or like anybody that wants to contribute to this. You can be, a graphic designer, you can be a data scientist creating a cool data set. You can be someone just has the data, doesn't know how to create, the data set. You can be a 3D graphics programmer. You can be, there's a lot of helps required, a lot of helps needed, and anything is welcome. So yeah, super excited about this. And as a conclusion, I just would like to quote, Raymond Kurzweil, which I had the pleasure to meet a couple years ago. And these are very inspirational to me. So it says Raymond Kurzweil is very famous because he makes a lot of different predictions, in the future. And some of them are super accurate, some of them a little less accurate, but still very inspirational. In 2019, the computational capacity of a $4,000 computing device is approximately equal to the computational capability of the human brain. And then the second one, in 2019, people experienced 3D virtual reality through glasses and contact lenses. And we already started witnessing that with the Google Glass project, which I hope never become a thing, by the way. But still, it's what I would like to say here is in 2019, seriously, it's like tomorrow. So we have to be ready, to integrate those devices into our data visualization techniques. And this is why we want to push it, to the next level with those new devices.
So just to summarize, Open Graffiti, free, open source, awesome data viz tool. You can use it to create any 2D or 3D models, and you can get it at opengraffiti.com. It's a placeholder for the GitHub repo. You can get all the information, all the files, all live there now. And so we've got some time left for questions. So thank you. If anyone has any questions, please let us know. All of the math and physics questions have to go to Thibaut. Yes, sir.
So we happen to be OpenDNS customers as well. We have a lot of data in our umbrella client. Can we visualize that data live to the API?
So he had a question of being able to visualize the OpenDNS data. You should be able to. Yeah, we should talk after.
I'm sorry, I'm not hearing you well.
I tried using particle physics to lay out graphs as well.
Yeah?
But in 2D.
In 2D?
And I ended up with unrelated clusters of data getting stuck to each other.
Okay.
Is that problem completely eliminated by going to the mixed thing you have?
Oh. I think.
So the question is, he had clusters that were, either not clustered together or too tightly clustered together, making it hard to articulate the data, and wanted to know if the tool solves the problem.
So usually, I'm not sure how you've done your process, but usually there's the temperature concept. So the temperature is pretty much going to control, how fast, how strong the force are going to be. And usually to get the best pleasing layouts, you'll have to have a temperature function that is going to start super high and go low very quickly, right? And maybe I have to look at it, right? But maybe your problem is that the temperature wasn't high enough, so the nodes cannot be, distinct from each other.
But you use some more physics than you actually do, right?
Oh yeah, for sure. The formulas that I'm giving are in 2D, right? So yeah, it had to be a little modified for the 3D version. Yeah, for sure. I can show you the formulas if you're interested.
Yes. So like a streaming, does it support streaming or dynamic data?
Yeah. So again, it depends how huge that would be. But for the dynamic part, absolutely, yeah, the force directed is super easy to use for that. If you actually add nodes, dynamically, the layout would just, auto expand itself. Well, I have to look closer at your problem. We can definitely talk after the presentation because that sounds like. But yeah, I guess there are many ways to, show the modifications. If you disconnect just two nodes, then pretty much the force-directed algorithm is going to separate them. But you can also change the color. That wouldn't change the structure of the graph. Or I'll have to look at your problem more precisely, to be honest.
But so the engine, if it doesn't work right now to support that, using OpenCL buys us, nearly infinite resources to do the rendering. So, given enough horsepower in systems, we can actually would probably expedite how fast we could show those dynamically added nodes and edges. Any other questions?
Yeah.
Repeat the question.
So the question is, besides all the features that we've shown, what control do we have on the layout of the graph? So there's what I call the visual API, I would say, and you can pretty much, you can pretty much talk to the engine to modify pretty much every feature that you need. But most of the features have been shown on the first graph, the abstract graph. So like shapes of nodes, edge width, like node width as well, node size, and the particle speed and like the circle speed as well. Yeah. So most of the features have been like shown in the videos, to be honest.
But one of the examples that we didn't show is one of the things that Thibaut did was the addition of like the mini maps or flags to the nodes based on their geolocation. Mm-hmm. So that's just one way to modify the nodes, provided you put it in your data set.
Yep.
Yes, sir.
For the crypto and alternate what you showed, did you get a chance to map through IP address instead of domain name to see, my fast flags or IP videos, for example? Did you get a chance?
So the question is, for the CryptoLocker dataset, did we get a chance to actually add the IP addresses of the domains in the datasets?
Look at the changes over time.
Yeah. Look at the changes over time. I can point you, actually, Ping over there is the one who worked on a CryptoLocker very precisely. She's made all the work. So you want to talk to her, to be honest.
Yeah. But for the visualization for this data set, it's a static data set. There's no reason we couldn't go back and get that information. It's just for the current data set we didn't do the time series. Yeah, there's no reason we couldn't apply the time series functionality to it. And even the diff graph to show, what has changed from date to date. So I think we have one more question. And sir, you had your hand up. So what kind of computer and GPU? So the hardware specs.
Mm-hmm. Yeah, absolutely. So most of the small graphs, you can run them on Mac OS X with a MacBook Pro. That's what I've used for like a year. So most of them you can run on them. You need an NVIDIA card. No, you don't need an NVIDIA, but you need a card that's going to have OpenCL acceleration, on the GPU, not only emulated on the CPU. So that's pretty much every graphic card. Yeah. You can use that. I've used it on Linux at home, to do the biggest videos. That was a graphic card that was like, as I said, 3 years old, something like that, GTX 550. So that's almost equivalent to the one in the MacBook Pros, in the last ones. Honestly, we just received a very nice visualization platform with the Titan, like NVIDIA Titan. I can't wait to try the performances on this one. But yeah, pretty much any laptop that has a decent graphic card, it's not super heavy.
Yeah, I've even run it on a MacBook Air, and it's a little bit slower, but it still does the trick. Obviously, the bigger your data set and the more complex your data set, the slower it's going to run. So you don't by any means have to run out and get like a new $8,000 computer to run it. It'll run fine on most standard hardware now.
Yeah. One more thing is you have to understand that there are two bottlenecks in this process. The first one is the physics, and the second one is the rendering. For the physics, you would probably not be able to expand the big like ASN network graph, for example, like on the MacBook. Or at least it would take a couple hours. But you will still be able to visualize it because the rendering is fast enough, right? But running the physics is the heaviest part here if you have a large data set.
All right, we're getting kicked off the stage now. Thank you for coming.
Thank you very much.
But we will be around today and tomorrow.